Hello, good morning all. I'm Amritan Chatterjee. Currently, I am doing my PhD in IIT Madras. I'm doing the course of Introduction to Photonics. So, as a part of this course, I'm making this presentation. So, in this presentation, I will make overview of the total course, whatever I studied and whatever I've learned. So, I will cover the entire course to this PPT. So, let's start. Introduction to photonics, this is the course name. So now, first we need to know this what is photonics. So photonics means it's basically deals with the properties and transmission of photons, that is through optical fiber, or it can be the interaction of the photons with the light and matter also. So we'll learn those things regarding the photons and photon interaction with matter and how the light can be transferred through the optical fiber. So that we'll learn in this course, and the different sources of the light and detector of the light, so that I will study. So now, why photonics? Photonics is the growing field now because its application is mainly on optical communication. It's the faster communication system that is going in this time now. Photonics is used in this optical communication mainly, and also whatever the camera we're using, CMOS camera, you need the photo detector. That is also the part of the photonics. Another application is the space applications, and it is also used in the biomedical applications for disease detection, and for the optical sensors also. So this entire photonics, it can be divided into means total four parts, I can say. That is four main regions of dealing with this photonics course. That is seen this year. So first one is ray optics, and the next broader is the wave optics, and after that electromagnetic will come, and then the quantum optics. Within the ray optics, we can deal some properties and some properties of light, but next we are not able to analyze some properties or some functions of the light. Then we need the wave optics. So as per the new functions and new characteristics, we need those these quantum magnetic optics and quantum optics. So we'll study those things by and by. First we'll study the ray optics. In ray optics, we'll deal with that light travels in a straight line. So light is a straight line, we can say, and Fermat is the first man who stated the statement. In this module, we will only consider that the dimensions of the objects is much greater than the wavelength of the light. In this module, we only can explain the two phenomena, that is law of reflection and law of reflection. Using the ray optics. So these two phenomena I can explain using ray optics. Law of reflection means incident light. It will be, if it is incident on a mirror, so it will be reflected back, and the angle of the incidence will be equal to the angle of the reflectance, and also they are in the same plane of incidence. So this is the law of reflections, and the law of refraction is the Science law that the light will be incident in between some two different mediums with n1 and n2 refractive indices is there. So it will be changed according to the Science law. That is equal to n1 sin theta will be into sin theta 2, where theta 1 is the incident angle and theta 2 is the refracted angle. So these two angles are related with the Science law. And as you can see, N1 and N2 are the two refractive indices. If N1 is greater than N2, so light will be moving outwards from this diagonal normal. So theta 2 will be greater than theta 1. And if light is traveling from N2 to N1, so it will be coming towards the normal. So theta 1 will be less than theta 2. So this is the Skin's law. So these two laws we can explain using the ray optics. And as we already told, the main contributor is Newton and Fermat. So in ray optics, we deals with different kinds of mirrors like planar mirror, parabolic mirror, elliptical mirror, and spherical mirrors that we have studied. So planar mirror is got the imaging property, and the parabolic mirror has the focusing property, and the elliptical mirror also has the imaging property, and the spherical mirror neither focusing on the imaging property. So this is the planar mirror. So you can get the image P1 in this using the planar mirror with a distance from the mirror. So these are the imaging property. Light will be reflected back, and if you trace it, you will get the mirror image of this P1. So this is the planar mirror characteristics, and the parabolic mirror, it has the focusing property. So if the incident light as parallel lights are incident on this parabolic mirror, it will be reflected back and it will focus to this point. So this is the focus point. So it has the focusing point. Now, if you place any light source here, and it will be reflected through this mirror, and you will get a parallel light. So these are the two properties of the parabolic mirror. So it can be used as a car light. So you can generate those parallel lights from the cars, and is used in telescope also for the focusing of the light. So you can see the image. Now the elliptical mirror, it has the imaging property. So you can see the 2 points, this P1 and this P2. So the light will be travel and reflected back from the mirror, and it will be focused on this point P2. Opposite also too, if you have a source in P1, it will be reflected back to the P2. So it has the imaging property. So it can be used for the coupling of optical fiber. So if you have a light source here, so you get the image in this point. So you can couple the optical fiber here. So that it can be coupled like that. Okay. And also it can be used for the decorative wall mirrors in the bathroom mirrors also. And the last is the spherical mirror. So it neither has the focusing property and nor has the imaging property. So different light will be reflected into different points. So only the light those are traveling through the very near the optical axis and make a smaller angle with the optical axis. So these are known as the paraxial rays. So these rays will be concentrated on, so can be focused in some point. So these are the paraxial approximation. So it can be used for the dental purposes. It's a concave mirror, and also is for the traffic purposes. There is convex mirror, so you can see those mirrors in the road also. So these are the mirrors we have studied, and next one is the ray transfer matrix. So this ray transfer matrix is used to describe optical system. So optical system means if you give some input light through any optical system, then light will be incident to the optical system, then it will be reflected by the different elements in this system, and at the output you will get some light. So you can relate this input light with the output light by this ray transfer matrix. So say the your input light, it has some height from the optical axis as y1, it is making some angle theta1 for the incident. And after traveling through those optical system and different mediums in this different systems, so you will get the output light as its height will be y2 and your angle will be theta2. So theta1 theta2 can be different and y1 y2 can be different. So this output ray can be related to the input ray using this using the ray matrix. So that is defined by this. That's y2 is a function of y1 and theta1. That will be a y1 and b theta2, and also theta2 will be function of the y1 and theta1. So it's a c y1 plus d theta2. So if you can represent in a matrix, you can get y1 y2 theta2 a b c d. These are the ray transfer matrix. This is the coefficient of the ray transfer matrix, and you will give the input and y1 and theta1. So if you know the system matrix, so you can get the output ray corresponding to the input ray. So this is the ray transfer matrix. So you can uniquely define any optical system using that. So main application of this ray optics, so you can say that we can build the ray optics using the optical fiber. So light will be travel through the optical fiber using the total internal reflection phenomena. So that comes from the refraction phenomena that we have studied in the ray optics. So Charles Cow got the Nobel Prize in 2009. So he got the Nobel Prize for the transmission of light through optical fiber. So now, so you can see if you see this is the optical fiber. So light will be incident into the optical fiber, and then it will be get totally reflected from the surface of this one is the core and this one is the cladding. So you have the two different indexes from the core and cladding. So generally, core has a more refractive index than the cladding. So N1 will be greater than N2. So again, the light will get total internally reflected from these two surfaces, and it will be reflected back again from this surface. So it can be confined by these two regions, and it will be travel like this. So optical fiber is a guided medium. It's made of silica. It used to guide the light. So in general, the core is made of silicon germanium and silicon dioxide and germanium dioxide. So which is refractive index 1.47, and the cladding has the silicon dioxide is a refractive index of 1.44. So using optical fiber, you can get 0.15 dB per kilometer of loss. So you can have a long distance communication using optical fiber, as the loss is minimum now. So optical fibers has replaced the coaxial cables for the optical fiber communication. So now we'll explain the total internal reflection. So that's the main thing in the optical fiber communication. So if the light incident in the two mediums of different refractive index N1 and N2 with angle theta1, it will be refracted with the angle of theta2. So now, as you increase this theta1, it will be coming towards this horizontal line, or you can say it's moving outwards from this vertical line. So at some angle theta c is a critical angle. You can say the theta2 will be 90 degrees. So this is the critical angle, and after beyond this critical angle, all light will be reflected back to this same medium N1. So this is known as the total internal reflection. So from Stain's law, you can got the expressions from the total internal reflection. If you make theta2 is a 90 degree, so you got this is the critical angle that will be equal to sine inverse n2 by n1. So beyond this theta c, all light will be reflected back in the n1 medium. So this is known as the total internal reflection. So you can see if the light is incident at the angle beyond theta c, it will be reflected back into this core. So again, it will be reflected back from here. if it is support the total internal reflection. So in this way, the light will be travel through this optical fiber like this. So this is the total internal reflection phenomena. Now, if we consider it's a cone of this type, so you can say this is the incident ray, incident beam in the optical fiber input. So it's making angle theta A. So again, it will be refracted through this optical core cladding interface. So it's making an angle say like theta C. So your theta A is the input and theta C is the refracted theta C bar is the refracted angle. So again, you can apply the Snell's law as you can consider this region as real. So you get sin theta will be n1 sin 90 degree minus theta c. From that, you get this sin theta angle that will be equal to root over of n1 square minus n2 square. So this sin theta is known as the numerical aperture of the optical fiber. So and if you take this angle theta a, it will be sin inverse root over n1 minus n2 square. This is the known as the acceptance angles or acceptance cones. So all the light will be falling into within this acceptance cones will be gathered by the optical fiber. It will travel to the total internal reflection. And beyond this angle, the light will be not get the total internal reflection. So after traveling some path, it will be lost in this core cladding interface. So this numerical aperture is the measuring quality. That's the light gathering capacity of the fiber. Okay, and this is the one important parameter you need to know about the optical fiber communication. And another thing is the optical fiber communication. We need to know the optical windows. Okay, so means the silica fiber has some attenuation loss characteristics with respect to the wavelength you are transferring. So this is the characteristic of the attenuation coefficient with respect to the wavelength. So if you change the wavelength, there will be different loss in the silica fiber. So you can see that at the wavelength of 850 nanometer, 13 nanometer, 1550 nanometer, you have the less losses compared to the other windows. So this is the region of 850. You have the Rayleigh loss and the scattering loss also. But in the 1550 nanometer, you have the less losses. So this is the main wavelength for the optical fiber communication. This wavelength is used. So in that wavelength, the optical fiber loss is 0.15 dB per kilometer. So you will get the least loss in this 1550 nanometer. So other you have got the Rayleigh scattering losses, absorption losses, and also the OH absorption loss. And for higher wavelength, you will get the infrared absorption. So lower wavelength, you will get the scattering loss and the UV absorption loss. So you'll get some transparent windows. So mainly we will do in this 1550 nanometer window the window for the optical fiber. This is for silica fiber. So if you use plastic, then the window can be changed. Now next part is the waveguide. So waveguide means wave will be guided through some medium. So optical fiber also is a waveguide. So you can make waveguide structure for the optical fiber optical communication. So for the light transmission. So you can make the structures so that your N1 will be greater than N2. So light will be confined to N1. So you can make some waveguide structures like this. This is the slab type structure where this is the core and this is the cladding. So this core has a more refractive index than the cladding. So this dark blue is greater than the light blue. So this is the strip type optical waveguide you can make, and this optical fiber is also waveguide. So and these are the different kind of waveguides you can make. So it's a straight waveguide. You have the S band waveguide. This is used for the guiding of wavelength. Then you can make a Y branch. It's kind of it can split light or you can combine light, and two Y type of shape can be merged to make this an extender. So it can be used as optical switch also. It can be used as phase and wave modulator that will be discussed later. And this is the directional coupler is to couple the from light will be coupled from this branch to the this branch or vice versa. So light power will be coupled between these two branches. And this the intersection kind of that you can make also. That is used for again modulation purposes. And next thing is the coupling of light means we need to couple the light so that it can travel to the optical fiber. So you can use some lenses to couple the light to the waveguide so that it can travel through this. And another type of coupling is the invert coupling. You can use directly light emitting diode or laser, so that can be used to directly couple to the waveguide. So it's the invert coupling. And also the prisms and grating are also used for the coupling of light. So these are the different types of couplers. And next important part is the fiber modes. So light will travel. Light is electromagnetic wave, so it will travel to the optical fiber in some different modes. Okay, so you need to know the different optical fibers depending upon the mode. So we have the single mode fiber, we have the multi mode fiber, with the greater index multi mode fiber. So this depending upon the if you this depending upon the refractive index plot in the core and cladding interface. So it's a step index multi-mode fiber. You can say there is a step change of refractive index. So this is the N1 is the core refractive index greater than the cladding refractive N2. So single mode fiber also has the step type of single mode fiber, but your core diameter is less for the single mode fiber compared to the multi-mode fiber. So they can support only one mode. And to minimize the losses in the multimode fiber like the and also the intermodal dispersions. There's a problem and delay of the different modes. So the solution is for the graded mode multi-mode fiber. So you can see the diffractive index profile is the graded kind of thing. That means it will decrease from the center of the code and it decrease towards the cladding. So this is used to decrease the intermodal dispersion that have the multi-mode fiber. And intermodal dispersion is less for the single mode fiber. It will not get intermodal dispersion. It will only get the intramodal and somatic dispersion. So that is not included here. So another important parameter is the V number. So depending upon the V number, you will get the different modes of the fiber. So V number is the measuring number. So it's defined as 2 pi by lambda into A into Na. N is the numerical aperture that we have studied only, root over of N square minus N2 square, where N1 is the co-diffractive index and N2 is the cladding refractive index. So N1 is always greater than N2. And lambda is the operating wavelength and A is the radius of the optical fiber. So if this P number is less than 2.405, you can consider this a single mode fiber. So any fiber is a single mode or multi mode. It's depending upon the wavelength and also the diameter, radius diameter. So you cannot say that this is a single mode fiber, something like that. So you need to mention the wavelength, which wavelength is after the single mode fiber. Okay. So if the wavelength is changed, your V number will be changed. So depending upon the fiber mode will be changed. So this is the important of the V number. So and this is the relation of the number of modes with the V number is 4V square by pi square. So last these two things I want to discuss. This is the parallel approximation what we have discussed earlier. For parallel approximation, the Snell's law will be reduced to n1 theta 1 will be equal to n2 theta 2 because sin theta 1 will be equal to theta 1 because angle theta is very small. So we can approximate this one. And these are the parameters for a single mode fiber. This is the core diameter 8 to 10 micrometers and the cladding diameter is 125 micrometers. So next we will move on to the web optics. Till now we have discussed about the ray optics. Now next we move on to web optics. So web optics is mainly deals with the objects whose dimension is almost comparable to the wavelength of the light. So previously we have dealt that d is much greater than lambda. So from the ray optics, with that condition we can have the law of reflection and law of diffractions. So the reflection and diffraction, these phenomena can be explained by the ray optics. But the interference and diffraction, these are the two phenomena of light that cannot be explained using the ray optics. So for these two explanations, we need to move on to the wave optics from the ray optics. So in wave optics, we deals light travels as a wave. So it deals light as a wave. So Huygens and Young, they are the two scientists who the main contributor in this wave optics as a light. So as you can see, it's deals with the wavelength of the light. Okay. So using the wave optics, we can define the diffraction and the interference phenomena. So this is the optical spectrum. So this is the visible range, is starting from 400 nanometer to 750 nanometer, from violet to red, and beyond red is the infrared and the ultraviolet. So our optical communication deals with from ultraviolet range to the infrared range, near in between. So is in this axis, your wavelength is increasing, so your frequency will be decreased, and also the energy will be decreased. So these are the things. And light travels in a medium air with velocity 3 into 10 to the power 8 meters per second. It's almost 2.99, so we can consider it as 3. And this is the relation between wavelength and the frequency. They are inversely proportional. So these are the spectrum. Okay, so this is the visible spectrum from violet to red. And these are the ultraviolet spectrum, near ultraviolet to far infrared. So near, mid, far, and extreme ultraviolet, these are the classification we can make. And it's infrared. So near infrared, mid infrared, and far infrared. So your optical communication range is from near infrared to ultraviolet range. So these will deal here. Now, if the light travels in a medium who's got some refractive index n, so then the wavelength of the light will be changed. So it will be decreased by lambda 0 by n, where lambda 0 is the free space wavelength. Same for the velocity also, it got decreased by 1 by n, and this is the wave number k. It got increased by multiplication of n. So it's light. It's in wave optics we deal with this wave equation. So here we can consider this wave. It has some amplitude and has some it's change with time. So it's a function of position and time. So we can define it as a u of rt. So this is the wave equation. So del square u minus 1 by c square del 2 u by del t is equal to 0. So where c is the velocity of the light in that medium. So you can see is light is characterized by a wave whose wavelength is lambda zero. If it is traveling through a medium whose has different diffraction is compared to the air, so it will be changed to lambda, which lambda zero to lambda zero by n. So this is the wavelength, the difference between the two maximum peaks. You can consider as wavelength. So we can express this URT as position. This is the position dependent part. This is the time dependent or frequency dependent part. So if you double differentiate it, you will get the minus omega square because you will get g omega. Then again it will be derivative, so it is minus omega square. So this wave equation can be reduced to this del square u plus omega square by c square into u is equal to 0, where omega by c is defined as k. This is known as the Helmholtz equation. This del square u plus k square is equal to 0 is the Helmholtz equation, and where k is the wave, you can see the wave number, okay, or wave vector, 2 pi by lambda, so omega by c, and intensity of light is defined as the magnitude square of this wave ur, so it can be defined as mod of ur square. So you have two types of waves. One is the planar wave, defined is this one is the planar wave, so you can have this expression. A0 will, amplitude will remain constant with respect to the distance r, and this is the spherical wave. This is the spherical wave nature. So it will, your intensity will be reduced with the function of r. As we move more towards the radius, your intensity will be decreased. This is the A0 by r. So these are the two expressions for the planar and circular spherical wave. And now we will move on to the two main properties that we can explain using the optics. One is the diffraction. Diffraction is the bending of light and traveling to the through narrow openings or the narrow aperture. As we can see, wave optics deal with the diameter of the object is closer to the wavelength of the object. So and this diffraction, we have the diffraction gratings. These are the main applications. So gratings can be used as in the filters and of the spectrometer. So diffraction gratings is some parallel plate of different thicknesses there. So you have got the different diffractive indexes. So if light will travel through this region, it will be get reflected depending upon the different wavelengths. So different wavelength will be reflected to the different angle to this diffraction grating. So using that property, you can make it as a spectrometer or use a filter also. So this one example is there. It will. This is the focusing mirror. Diffraction grating will be make the different colors of light. So you can have the CCD array. So you can detect the different light also. So as I told, it's a periodic structure, different thickness that split the incident wave into multiple waves. So different wavelength, you have the different incident wavelength. So it will be reflected to the different angles to these slits. Okay, so different wavelength has making different angles. So that's why they are splitted. You can see the RGB is splitted here, and this is the white light. If it is incident white light, it will be split into different lights. So it can be used with the optical spectrometer, so you can get the spectrum, and also it can be used with filters. So if you can place the detector depending upon the angle, you can get the filters. You can filter the different kind of wavelengths and light also. So what is interference? Interference is basically the superposition of two waves. So if the two waves are generated, so they will interfere with each other, and they will generate the output waveform according to the angle or the phase difference between these two waveforms. So as you can see, there are if the two waves are emitting from these two pinholes, the two circular waves are emitting, so they will be interfere with each other, and accordingly you will get the output waveform at the maximum and minimum of the output depending upon the phase difference between the two waveforms. So the total intensity output will be equal to I1 plus I2 plus 2 root over I1 I2 cos phi. So where I1 and I2 are the intensity of the two waveforms, and phi is the phase difference between these two. So if the phase difference is 0, so you will get the constructive interference at the output, and if the phase difference is phi, you will get the destructive interference, so you will get no output. So basically, you will get a alternate bright and dark spot here. So this is the formula related to this Young's double slit experiment. So this is the d sin theta will be equal to m lambda, where m is the position or the position of the minima from the center, and lambda is the wavelength, and d is the slit separation. Okay, the small d is the slit separation, and sin theta is the angle is making with this angle of the wave that is making with the center of the line. Okay, and so from these two relations we can say if the first minimized distance is say y, so y by d will be equal to tan theta. So that tan theta can be approximated as sin theta. So this is the relation. So m is the position of the minima. If it is first minima, then it should be 1. So from that you can calculate the slit separation from measuring the maxima and minima from the output screen. You will get waveform like this. So at 0 and 2 pi and 4 pi, you will get the maximum intensity, and for odd multiples of pi, you will get the minimum intensity. That is the destructive interference, and this is for the constructive interference. And now the application of interference is the interferometer. So interferometer is basically a device that can split the optical wave input beam into two different beams, and it will be delayed by some elements, and they will be reflected back through some mirrors, and again they will be interfere with each other, and depending upon the phase they will get the output. You have the beam splitter, you have the reflector, and you have the beam combiner also. Three different kinds of interferometer. One is the Michelson interferometer, one is Mach Zehnder, and one is Sagnac. So these are the three classes of interferometer we will discuss. So first one is the Michelson interferometer. This is the schematic diagram of the Michelson interferometer. So the incident light is there. This is the beam splitter. So this will split the beam into these two directions. You have these mirrors. This one is mirror one. This is mirror two. It will be reflected back to this beam split. It will combine, and we will get the output from here. This is the Mach Zehnder interferometer. Again, you have the beam splitter. Two beams will be split in two direction. It will travel two different paths, and again it will be reflected back and combined here. You will get the output from here. This is the Sagnac interferometer. So it will be splitted again. Beam splitter will split the two lights in two different direction. So the light will be traveled in two different direction. One is this way, and another one is this way. So depending upon this rotation or direction, you will get the output at the output from the beam splitter. So this all the interferometer is the main mechanism of interference, and depending upon the angle between the two waves, you will get the constructive or destructive interference patterns. So this first we will discuss the Michelson interferometer. So Michelson interferometer is main application is for the OCT, optical coherence tomography, and also it can be used for the measurement of it can be used for the displacement measurement. So one mirror you can move, so accordingly your interference pattern will be got changed because the path difference will be different, so you get different phase differences. So accordingly your interference will be changed, and it can be used for the measurement of refractive index. If you insert any medium here, the refractive medium here, so that will change the path difference. So you can measure the refractive index in this Michelson interferometer. And optical coherence tomography means you can measure different levels of different properties. So if you see this, if this is the detector, so light will be splitted here. This is a movable mirror, and if this is the sample, it has different concentration and different levels. So light can be reflected from different mediums. Okay, so according to adjusting this mirror, you can see the characteristics of different layers. So that can be used for checking the eye also. So this is the one application, and this is the relation between the movement of the mirror with the pattern. Okay, so this is the wavelength and this is the number of fringe patterns. So if the distance of the mirror can change, you will get at the output, you will get some fringe pattern. So that pattern will a number of counts and number of fringe pattern pair that can be changed using this movement. So if you move this mirror d, the total movement will be 2d. So this is the relation d is equal to n lambda by 2. So from that you can measure the displacement, or you can measure the wavelength also. So different thing you can do. Now next is the Mach Zehnder interferometer. It can be used as the intensity modulation and optical switch. It can be used as a modulator. It can be used as a switch. So this is the waveguide diagram of the Mach Zehnder interferometer. So in any of the branch, you can insert a medium of different refractive index. So the path difference will be different. From that, you will get the output according to the phase difference. It will be constructively or it will be destructively interfered. So if the input light is travel these two branches, you have different material here. So it has different refractive index. So the path difference will be different. So at this moment, they will be interfere. So at the output, you will get the output depending upon the path difference and depending upon the phase difference. So this is the relation of the path of the Mach Zehnder interferometer with the fringes pattern. So if this reflecting index n1, this is the reference arm. So this reflecting the difference will be related to these relations. And phase difference of this branch, these two branch will be related to 2 pi by lambda into del n effective into L. So L is the length, and this is the refractive index difference between the reference arm and the measured arm. So from that you can measure the angle, and if the angle is 0 degree, you will get the constructive interference, or if the angle is pi, you will get the destructive interference of 0. So it can be used as optical switch. So if these two differences are 0 degree, you will get the optical output, and if this difference is 0 degree, you don't get any optical output. So it can act as a switch. I will get output for one, and for the next time it will not get the output. So it can act as a switch. So it can be as a thermo optic switch, because if you change the temperature, you can change the refractive index also. So this is If you change the temperature, effective index can be changed. So you can make a thermoptic switch, and also on the electro-optic switch also, if you change the some materials will be there, you can place here. You can change the electric field, you can change the refractive index accordingly. It can be used as optical switch also. And the Sagnac interferometer main application is the gyroscope. So it can be used to detect the rotational movement. So it's related with the rotational movement with the phase difference. So if you have a source and this is the coupler, and you have this optical fiber, and light is traveling by this coupler will be divide the light into two different lights, and it will be traveling to two different path. One is clockwise and another is counterclockwise. So if this total system is at rest, the counterclockwise and clockwise, these two waves will be reaching at the same position. So there will be no phase difference. Now, if you rotate this system, so you have the different path difference for the clockwise and counterclockwise wave. So if you move the system in clockwise direction, the clockwise wave have to travel a longer path compared to the counterclockwise path. So you have a phase difference in that. So from the phase difference, you can measure the angular rotation. Okay, so this is the relation. This is the phase change, and this is the relation of the phase change with the angular momentum, where A is the area, pi into r square, r is the radius of this total curvature, and the n is the number, n is the number. So number of turns is there. So total length will be 2 pi r into n. So this gyroscope is used for the optical gyroscope. It can be used for the Sagnac interferometer, can be used the gyroscope. So you can measure the rotational movement. So these are the applications of the wave optics. So wave optics can able to describe the interference and refractions pattern, but it failed to describe the property, that is polarization. So for that polarization, we need to move on to electromagnetic optics. We have covered the ray optics and the wave optics. So now we'll move on to the electromagnetic optics. So now, what is the need of electromagnetic optics? So ray optics and wave optics are able to describe the reflection, refraction, and also the interference refraction phenomena, but they fail to derive the division of light from the beam splitter. Okay, so this can be explained by the electromagnetic optics. So this depends upon the polarization of the light. So depending on the polarization of the light can be splitted. So polarization phenomena cannot be explained by the wave optics. So which wave optics deals with light as a scalar wave. So polarization deals with the direction of the electromagnetic field. So we need to consider light as a vector quantity. So that's why we need to move on to the electromagnetic optics. So basically, polarization means the direction of the electric field with respect to, for any time. So this is the time course of the electric field. We will trace the electric field direction. So Maxwell is the main contributor here. So he states that light travels as an electromagnetic wave. So basically, light. He told that light consists of electric field and a magnetic field, which both are perpendicular direction, and light will travels to the perpendicular direction of the E field and H field. So if E field is direction, magnetic field will be 90 degree, and the direction of propagation will be 90 degree. So this type of wave is known as the transverse electromagnetic wave, as both all the electric field, magnetic field, and direction of propagation, they are all perpendicular. So velocity of the light in free space as the electromagnetic wave is formula is root over of mu 0 and epsilon 0, where mu 0 is the permeability of the free space and epsilon 0 is the permittivity of the free space. Electromagnetic optics mainly deals with these four equations proposed by Maxwell. So the first was the Gauss's law. There is divergence of E and divergence of H is equal to 0. So that is means if you the total flux coming out from a closed surface, that will be 0 if it does not any enclosed any electric charge, and the total flux coming out from a closed surface, the magnetic field, that is equal to 0. So that means there will be no magnetic monopole can exist. This is the Faraday's law. The curl law B is equal to minus mu 0 del H del T. That says that change in magnetic field will generate change in electric field. So that electric field is opposing the change of the magnetic field. That's why the minus sign is there. And Ampere's law states that change in electric field can generate change in magnetic field. So these are the four equations. So this is valid for in the free space, where E is the electric field and H is the magnetic field. So we can write the electric field. This is a vector. So it's the position and the time dependent one, also for the magnetic field also. So these are the values of epsilon 0 and mu 0. So we can explain this H and R. This is the position. This is the magnitude part, and this is the exponential phase part. So if the light travels in a medium, say a dielectric medium, then the property and also the equation will be changed accordingly. So these are the equations for the medium, dielectric medium, where H is the magnetic flux density and D is the electric flux density. They are related with this relation. So the magnetic flux density is related to the magnetization property, and electric flux is related to the polarization property. So if you apply the electric field in this medium, so it will generate some polarization property for the electric field. So this is the relation of the polarization. So basically, if you the polarization and electric field is related with this relation. So basically, polarization and electric field they are proportional. So I so it will be equal to epsilon zero into pi into epsilon electric field E, where this is the susceptibility of the medium. So if you start with this, so you can get the relation of this electric field with the polarization field. So as you know, so this is the refractive index that will be equal to c0 by c, the velocity of the free space light wave and the velocity of the medium. So we can write it in terms of mu and w. So it's a non-magnetic material. We can neglect this. So it will be epsilon by epsilon zero. So epsilon by epsilon zero, we can make it 1 plus psi is susceptibility. So we can write the refractive index is equal to power 1 plus psi. So, and this is the impedance of the medium, ratio of the electric field to the magnetic field, that will be equal to root over of mu by epsilon. So from here we can see that if any if light travels in a medium, it will generate some polarization property, and the polarization can be changed or something like that. So polarization is an important thing. So we can write the electric field expression is with this equation. So this is the traveling component. This is the propagation component part, and Ex and Ey are the electric field component in x and y direction. And this phi is the phase difference between this x component and y component. So if the phase difference between these two are 0 degree or pi, we can consider this a linear polarization. Okay, so light will be linearly polarized, and if the phase difference is plus pi by 2 or minus pi by 2, we can consider circular polarization. That means the electric field vector will trace a circular path, and for linear polarization path, it will trace like a linear path. Okay, and if Ex equal to Ui, then it will be circular, and for any other value, you will get an elliptical polarization. So light will traverse like the electric field will traverse like a elliptical path. Okay, so there are two types of circular polarization. One is right circular polarization, one is left circular polarization. If the phase difference is pi by 2, we will get right circular polarization. So electric field wave will be rotating in the clockwise direction, and if it is minus pi by 2, electric field wave will be rotated in the and counterclockwise direction. So these are the all type of polarization. This basically is the time course of electric field. This is the trace of the electric field vector. So if light electric field is incident in some medium, and it will be passing through the medium, so the polarization will be get changed according to the medium property, according to the property of that. So if electric field incident vector is a1x and a1y in the x and y direction, so at the output of the medium we will get a2x and a2y. So these two are related with this matrix parameter, that is T11 and T12. This is known as the Jones matrix. Jones matrix. So this will be A2x, this will be A2y. So x will be first and y will be later. So this is a mistake. So A2x by A2y, this will be T11, T12, T21, T2. This is the metric representation, and 1x, A1y is the input electric field vector. So accordingly, we'll get the output electric field vector. This is the relation. So if you know this Jones matrix, you can get the output vector of the electric field if you know the input vector. So this is an example. If Jones matrix is like this, so if your incident electric field in form is like this, so it will pass through this polarizer. So it will get linearly polarized, and only the x component will be there. So it will be suppress the y component. So y component will be zero. Okay. So polarizer basically allows some specific direction of electric field, and it will block the other direction of the electric field if it doesn't match. So it's a function of the polarizer. Now, next part is the wave retarders. So, retarders is a device that can be used to change the polarization of the light. Okay, polarization of the wave. So, this is the matrix representation. So, it will generate added some extra phase difference between these two. This is the minus J5. So, this is the retarders of the this plate. They have some two axes. One is the fast axis and slow axis. So in fast axis, the wave travel faster, and the slow axis now wave will travel slower, because the refractive it is depending on the refractive index. So in fast axis, refractive index is less, so light will travel faster, and the slow axis refractive index is high, so light will travel lower. So by this, it will change the polarization. So there are two types of wave retarders there. So one is quarter wave retarder, one is half wave retarder. Quarter wave retarder it will change the one polarization to the other polarization, like the linear polarization. It can be changed to the circular polarization, and also the circular polarization can be changed to the linear polarization. So this is the function of the quarter wave retarder. And half wave retarder will maintain the polarization at the same type of, but it will change the angle of the polarization. And that means if input you will get the linear polarization, and output you will get the 90-degree phase shifted linear polarized light. Okay, so this is the 90-degree phase shift between the input and output if you pass to the half wave data. And if you pass the circular polarization light, so it will convert it to the opposite circular polarization. If the input is the right circular polarized, it passes to the half wave data, you will get the left circular polarization. So these are the retarders. So they are used to change change the polarization of the light. They are the devices, optical devices. And another one is the polarization rotator. So it can it's a device that can rotate the polarization. It will make the polarization same. So it can make some angle with the input and output. So if you give some input polarization, and it will be rotated with some theta angle depending upon this matrix. So these are the part of the retarder portion. So now we will discuss about the some reflectance and transmittance coefficient of the electric field vector. So if this is the two medium N1 and N2, where N1 refractive index is greater than N2. So light is incident into this medium. So some will be transmitted through this medium, some portion of the light, and some portion will be reflected back to the medium. So theta 1 will be equal to theta 3, and theta 1 and theta 2 will be according to the Snell's law it will maintain. So as you can see, this incident electric curve has two components in x and y direction. So same with the x and y direction component will be there for the refracted and reflected wave. This is the wave vector k. This is the direction of the wave traveling. So we will find the relation between the incident wave to the reflected wave and incident wave with the transmitted wave. So uh, this is we can consider the E2 and E2x and E2y as the transmitted electric field vectors from the x and y direction, and E3x and E3y are the reflected vectors. So they are related with the reflection coefficient is Rx and Ry. Rx is the x direction, Y is the y direction, and the two E2 and E2 are related to the transmittance coefficient. So this is the metric represent this is the transmittance matrix, and this is the reflection matrix. So these x and y are independent, so that's why there is a diagonal matrix you will get. And one you think need to know, this is the T and Tm polarization. So what is T polarization? So the x component of the electric field, this is known as the TE polarization, or you can say the electric field is perpendicular to the plane of incidence. So it's the TE polarization known as. Also it can be sometimes is known as S polarization. And the y direction of the electric field is known as the Tm polarization, or you can say the electric field is perpendicular to the incident, or you can say the magnetic field is perpendicular to the plane of incident. So this is the TM polarization, and the y-axis is the TE polarization. So we'll check for the both TE and TM polarization. So Rx is the reflection coefficient. Is for the is x means is the for TE polarization mode. This relation is n1 cos theta minus n2 cos theta 2 by n1 cos theta 1 plus n2 cos theta 2, where theta 1 theta 2 theta the transmitted angle, and n1 and n2 the refractive index. So and, this is the transmittance coefficient related to the this relation, and this is for the TM polarization TM reflection coefficient. So relation is this one, and Ty is the Ty is the reflection coefficient of the TM. So these are the relations. So you can get. These the two important applications are the external and internal reflections. So when you are talking about the external reflections, we will consider that N1 is less than N2. This N1 is less than N2, and so we'll check the reflectance coefficients for the T here. Okay, so you can check from this equation that if the incident angle is 90 degree, then your reflectance coefficient will be equal to 1. So it will start from some value. If it is, you can check here. So if you put theta 1 and theta 2 both are equal to 0 degree, so it will be n1 minus n2 by n1 plus n2. So as n1 is less than n2, so Rx will be always as a negative sign. So it's you got a 180 degree phase shift. Okay, so the phase is always 180 degrees, the pi s. So it will pi for it will remain pi 180 degrees, so 0 to 90 degree. And if you put theta 1 as 90 degrees, so you will get Rx is equal to minus 1. So at 90 degree of the input incident angle, you will get the reflections as well. So when the input wave is incident of the 90 degree, it will be totally reflected back to the second medium. Okay. This is the reflection coefficients. And if it is internal reflection, then n1 will be greater than n2. So n1 is greater than n2. N2 means we will consider the total internal reflection, because it will be incident here, and it will be reflected back to this medium by the total internal reflection, because n1 and n2 are different. Incident angle theta 1 is greater than theta c. Then theta, if this one is theta 1, so if it's greater than theta c, then your total internal reflection will happen. So you get the reflection coefficients as 1. And if it is greater than theta c, so your uh, phase will be increased from 0 to negative degree, and at 90 degree you will get the minus 180 degree phase shift. So it will increase like this. Okay. And this is for the TM. The first one is the for TM. This is for the TMR we can consider. So this is the external reflection. So this you can see at some angle your at some fixed angle your RY will be 0. So this is known as the Brewster angle for the external reflection. That at that, if the light incident at that at the Brewster angle, you will see that RY will be 0. That means the your TM polarization output waveform will be 0. There will be no TM polarization output at the Brewster angle. So the Brewster angle is defined as n inverse n2 by n1. Okay, so if incident under theta 1, R1 will be 0, that means there will be no TM wave. TM polarization wave will be suppressed at the output. So you will not get any Y component. That means TM wave will be not there. Okay. And if you make it more than booster angle, then it will again increase to 1. And at the booster angle, the phase will be also changed from 180 degree to the 0 degree phase shift. So if you can put the values, you can check. Main application of the booster angle is to make polarizer like polarization sunglasses and polarizer for the lenses also camera. So using sunglass in the sunglass, they using the booster angle principle to reduce the reflection from the sun ray that is reflected from the roads and some other places also. And for the camera lens, use the polarizer so that light will be not reflected here and there in the lens. So these are the applications for booster angle. Also for underwater imaging, booster angle principle is used to make those glasses and so that you will not get any reflected waves. Okay. And the last one is the Malus law. So Malus law is state that if polarization light is passed through a polarizer, so it will pass to some specific polarization according to the axis of this polarizer. So after that, if you place any analyzer or the medium, so if it is rotated at theta degree, so your incident light will be passed only that angle of theta, that is E cos theta will be passed and E sin theta will be blocked because it is matching with the axis of the polarizer. So the intensity is related to the electric field potential square of the magnitude. So intensity will be equal to the this E0 square into cos square theta. So it is related, the intensity will be equal to the incident intensity of cos square theta. So this is the Malus law. It will be related to the cos square theta. So if the theta is 0, so you will get the total intensity. It will be not any nothing will be lost. So total intensity will be passed. So and if the polarizer rotates to 90 degrees, so it will light will be and it will be blocked all the polarization. So you will not get any light at the output. So the intensity will be 0. So this is the polarizer. You can make the polarizer to make it. It's a random polarization light. You will get some linear polarizer if you use a linear polarizer, and then if you rotate another polarizer analyzer is some angle theta, so you will get the output of the T on theta 1. So this incident you will get the square I0 into cos square theta is out. So if you change the polarization or the polarizer angle, so you can change the intensity. We have come to the last topic. There is quantum optics. The last topic, but last but not the least. So it's the most important topic, and the going field is the quantum optics. So this can explain the every phenomenon of the light. Okay. So after this, we have discussed about the wave optics, and electromagnetic optics that can explain the law of reflection, refraction, and also the interference diffraction property of the light, and also the polarization property of the light. But all the module we have discussed, all the things we have discussed, they are able to describe the two main important things. That's the one is the absorption, emission property, and also the photoelectric effect. So how the light is absorbed and how the light is emitted. Okay, so these are the main two topics. They cannot be explained using those the electro optics, wave optics, and electromagnetic optics. Okay, so after this we have discussed considered light as a continuous wave. Okay, so last we have considered the light as electromagnetic wave, but we have considered light as a wave. Okay, so now in quantum optics we considered light as light consists of particle. Okay, so it has both the particle nature and also the wave nature. Okay, so Max Planck and Einstein, they are the main contributor in the quantum optics domain. So Max Planck is first stated that light emission absorption is quantized. Okay. And Einstein says that light comprises quanta of energy. So light itself is a quantum of energy. So what is quantum? So quantum means it's a discrete electromagnetic wave. Okay, so there has momentum and energy, but it has zero rest mass. Zero rest mass. Okay, so it has the wave property, it has the particle property, photon. So it's a wave particle duality thing. So it has both the properties. So we will discuss now. Consider light as a discrete quanta of energy. Okay, that is the photon. So light consists of photon particles. So we can now within this module we will consider light as a particle. Okay, so it is interact with the matter, so you can consider it as a particle sitting. So accordingly, it will come across this absorption, emission, and those photoelectric phenomena. Okay. So photon has some energy, so that will be related to this E is equal to h nu, where h is the Planck constant, nu is the frequency of the light. So you can write it hc by lambda also, where c is the velocity of the light. So in free space it is 2.99, so you can consider it as 10 to 10 to the power 8. Okay, and h is the Planck's constant. This is the value of the Planck constant. If you convert everything to electron volts, so you can find this relation. This is the most important relation. So E will be equal to 1.24 by lambda. Lambda is in micrometer, so energy will be in electron volts. So if you want to replace lambda in nanometer, it will be 1 to E0 electron. So if you know lambda of the photon, you can get the energy of the photon. Okay, or you can know as you can consider the light is consist of photon. So if you know the wavelength of the light, you can get the energy of the light. Okay, so if you know the energy of the light, you can find the wavelength of the light also. So interaction of photon with matter means how light will interact with matter. So now we'll see. So light is a photon. So how the photon will interact with the matter. E is equal to h nu. So it has some energy. So if it hit any say material, okay. So let's this is the material who has a band gap, okay. So this is the valence band, this is the conduction band. So the difference of the energy between the valence band and conduction, this is known as the band gap of material. So if you can have semiconductor, you can have metal and also insulator also. But insulator the band gap is more, and in metal there is no band gap because electron and holes they will lie touching each other. So and so mainly we'll deal with the semiconductor devices here. So if the light hit any material whose a band gap that is Eg. So if the light energy that is H nu will be equal to Eg, so that light will be absorbed by this material. Okay. So how it is absorbed? So the electrons will generally stay in the valence band. So these are the outer cell of the atom. So they will stay in the valence band. So if the light is heated, light will incident in this material. So what will happen? Electrons will move from the valence band to the conduction band by taking the energy. Okay, so light will be absorbed. So this is the absorption phenomenon. So photon will be absorbed if the photon energy matches with the band gap of the energy. Three main part will discuss of the interaction of photon with matter. One is absorption, one is spontaneous emission, and another one is the stimulated emission. So absorption I have already discussed that if the energy of the photon will be equal to the band gap, light will be absorbed. Now what is spontaneous emission? So if there are a lot of electrons in the conduction band, okay, so conduction band is the higher energy level compared to the valence band. So electron will always stay into the lower energy level. So they are more stable in the lower energy state. So they used to lose the energy and come back to the valence band. So this is the band gap of the material. So if the electrons are staying in the conduction band, they will spontaneously jump to the valence band, and it will emit some energy that is h nu that will be equal to the band gap. So this is the spontaneous emission you can consider because the electrons are spontaneously emitted from the conduction band to the valence band. It will generate the equal amount of light. And next one is the simulated emission. So if the conduction band has a lot of electrons compared and the valence band has holes. So if any photon of energy h nu strike hit this material, so electron will jump from the conduction band to the valence band, and it will generate another photon of with energy same that hit the material. So if h nu energy of the photon is hit the material, so it will generate same amount of energy and same wave, same photon. So if one photon hits the material, it will generate two photons of the same energy. So this generated photon, the clone photon, which have the same frequency, same wavelength, and same direction of propagation. Okay, and it is the same phase, so it is known as the coherent. Okay, so this phenomenon known as the coherent. It has the same phase difference, or it can be a fixed phase difference. This is known as the coherent phenomenon. So that this is the clone photon. Okay, so these are the three phenomena. So we'll by and by discuss all these phenomena when we're discussing about the devices and what it will be matter. So absorption, spontaneous emission, and simulated emission. These three are the main part of the quantum optics. So in the absorption phenomena, the application is the absorption spectroscopy. So here we check the response of any matter or material with respect to the incident light. So this is the property of the any matter or material. It's a wavelength dependent property. So from that we can measure the property of the material. We can detect and we can make a lot of things from this. So if you say P0 is the incident power and P is the transmitted power. Transmission coefficient can be related as P by P0. This is the transmitted power divided by the incident power. And the absorption coefficient we can relate, or the absorption we can relate it as incident wave divided by transmitted wave. So this difference is basically the light absorbed here. So the energy absorbed here. So this can be related minus log T will be equal to epsilon BC. This is the Beat's law of absorption, which is related to the absorption. How much light is absorbed is related to the concentration of that material. So if it has the thickness of B and it has the concentration of C, so the absorption percentage absorption is related directly proportional to the concentration. So if the concentration of the material is increased, it will absorb more and more light. So this is the Beat's law. So absorption spectrum is spectrometer. So we can this is we have already discussed. So this wavelength dependent property of any material we can check here. So there are two types of absorption spectrometer. One is the single beam absorption spectrometer, where it is the source of light and filter that light to make it a monochromatic light. So this is the reference cell. So the light will pass to the reference cell. So some portion will be absorbed or some will be transmitted. So some portion will be transmitted. So you will get the measure the intensity in the photodetector. Now you will use the sample here. So the sample will absorb the light differently compared to the reference. So with this reference, we can calculate the how much light is absorbed by the sample and how much it can transmit it. Okay, there will be a change in the spectrum also. Okay, so this will absorb some light and this will transmit some light. So that you will get some transmittance peak. Okay, and you will get some absorption peak. Okay, So some light will be transmitted through this medium, some wavelength will be not transmitted to the medium. So you can check the medium property or the material property according to the incident light. And next is the double beam spectrometer. So in single beam, we need to place the first reference cell, then need to place your sample cell. So you need to compare these two. So you are manually placing it, so there will be some error is there. So therefore, the improvement of that, we use the double beam spectrometer, where you don't need to place the sample and reference one by one. So they are placed together and they are intact. So you use the light source, they will filter. So you are using beam splitter, so the light will be splitted by two parts. So one will be travel to the reference cell, one will be the sample cell. So this is the difference sample. We will calculate the difference. So you will get the absorption value, how much is light is absorbed by the difference of this. Okay. So another application is the fiber beam spectrometer using the diffraction grating. We have already discussed the diffraction grating can use the spectrometer. So if the light is travel through here, it will reflected back and it will pass through some grating. So it will be light different light will be different light will be different will be diffracted by the different angles. So you can get the spectrum of the light. So it can be used as a spectrometer. The spectrometer we can use to detect some in medical disease detection also. According if some good cell is they can absorb some specific wavelength, and if it has some cancer or something like that, your absorption peak or transmittance peak will be changed. So from that you can diagnose or detect the disease also. So this is one application. Now, next important another part is the fluorescence, the quantum optics. So fluorescence is basically it exists. So it's some specific material that has the fluorescence property. They are known as the fluorophore. So basically, if you shine a light with this fluorophore, so it will emit a different wavelength of light. So you incident away from like a specific wavelength like this, and the fluorophore will generate another wavelength. Okay, so generally it will generate a longer wavelength compared to the incident wavelength. Okay, so the your peak will be shifted. This is the incident peak, and this is the generated peak. Okay. Rhodamine, cyanide, these are the materials which have the fluorophore property. Rhodamin B and Rhodamin 6Z. If you incident with the green light, it has shown the fluorescence property. It will emit orange and yellow type of light. Okay. It can be also used for the cancer detection. If you incident a light or a photon with some energy. Okay, this is electrons are in the ground state energy. So yeah, getting those photon energy, it will be absorbed and it will be excited to some higher energy level. So it has some different energy levels. So it will be excited to the higher energy level, and then they cannot stay at the higher energy level for a long time. So this is the short duration. So they will lose that energy and come to the some another energy level, lower energy level. This is known as the metastable state. So this is the vibration relaxation state. So here the electrons can stay longer compared to the higher energy levels. So from here it will jump to the lower energy level. It will generate the according to the wavelength. So as you can see, the incident light has the more energy. So it has more energy. So your light electron will be from the ground state really going to the excited state. Okay. So it has a lambda is less. Now it has coming to the lower energy state. So the energy difference is low. So your lambda will be more. So generally the fluorescence, the fluorescence generated light or emitted light or waveform is more than the incident waveform. Okay. This is the generated waveform is better than the incident waveform. So this is the state diagram. Absorption is a very fast process. It's 10 to the power minus 15 seconds. Okay. So in the electron will be very fastly emitted and we go to the excited state, where this is the vibrational energy level. So this is the short state. So they decay to the lower energy state, that is the metastable state. You can say they are this time difference is 10 to the power minus 40. So this is also a fast process. And from this energy to the lower energy level, it's a comparatively slow process. It will take into the 10 to the power minus 7 to 10 to the power minus 5 seconds. So this is quenching, means this energy is lost as a heat. It will not generate any light. And another process, the timing is 10 to the power minus 9 seconds, is a nanosecond to microsecond rate. That will generate the fluorescence property. So that will have the fluorescence property. So it's in the nanosecond to microsecond range. So you will get the fluorescence light emitted here. And there are some interstate change also that will take around 10 to the power minus 10 to the power minus 8 seconds. So this is the excited triplet state. So between these two, the orientation of the spin number can be changed. So accordingly, there are electrons as in spin number also. So the photon spin number got changed, rotated. And when it is from excited state to the ground state, then again it will be converted to the original spin number. But this triplet state to the ground state is this is take a longer time, so around uh, millisecond to some thousand seconds. So this is known as the phosphorescence property. So some material shows the phosphorescence property and some material shows the fluorescence property. Fluorescence is a very instant process. You will instantly see the fluorescent light. Okay, whenever you shine the whenever you shine any light to the fluorophore or fluorescence material, you will see the fluorescence light emitted from you at the same instant. But for phosphorescence, you will not see at the same time. So it can be after some hour or something like that, you will get the phosphorescence output, phosphorescence light emitted. So if you shine the light to the fluorescence material and phosphorescence material, and you turn off the light, you will not see any light for the fluorescence material because it instantly generated and instantly gone. But phosphorescence, you can after making the dark room, you can see the light generated because after some millisecond or some thousand second, the light will be generated. The phosphorescence property will be shown. Now we'll move on to the devices. So we will deal with these four devices basically. So these are the light generator devices, and this is the how to detect the light, and modulator means you can modulate the light. Okay, so these are the components used for the optical communication. LED and laser, they are used for the generation of the light, and photodetector is used to detect the light, and modulator is used to modulate the light. How you can modulate the light. Okay, we'll start with LED. So light emitting diode. You all know about the LEDs. So we come across the LED nowadays. So they are replacing the normal tungsten light and bulbs. So the LEDs are more power compared to the tungsten light and the normal fluorescent light, and it has low cost. Reliability is more. So and for short distance communication also, LEDs are used around 100 Mbps or 10 Mbps kind of thing. So now, what is how you can make LED? So LEDs can be made from PN junction diodes. Okay, so if you have a PN junction diode, so this is the PN junction diode. So if you make it forward biased, so what will happen? The hole will be flowing from the P side to the inside, and electron will be flowing from the inside to P side. Okay, so if there is a PN junction, you have the depletion region here. So this is the inside depletion region. This is the P side depletion region. So you have the internal electric field from inside to P side. So whenever you are applying an external electric field, so this barrier potential will be reduced. So electron will from inside to p side, and holes will be from p side to inside. Now when they are flowing, they will recombine with each other near the junction. So as they are recombining, it will generate light. So basically, electron hole recombination, it will generate lights. Okay, this is the main thing. But now normal pin junction diode does not emit light. So what is the difference? So in case of normal pin junction diode, they are the indirect band gap semiconductor using. So silicon is the indirect band gap semiconductor. Germany was an indirect band gap semiconductor. So in case of indirect band gap semiconductor, they does not emit light. Okay, so they will only generate phonons. So as you can see, if you see the energy band diagram, so if you see the energy band diagram, so this is the whole EV is the valence band. This is the conduction band. So valence band has the lot of holes, and the conduction band also has lot of electrons. So if the electrons from the conduction band jump to the valence band and recombine with the holes in the valence band, you will get light from generator. H nu is equal to the band gap of the material semiconductor. So LED has a broader spectrum. Okay, so it's a spontaneous emission. LED has a spontaneous emission that we have already studied. So electrons are spontaneously recombined with the holes. So it's spontaneous emission. So it is a broader spectrum, and this only happen for the direct band gap semiconductor. So direct band gap semiconductor has the conduction band and valence band. They are lying with the same vector k or the same momentum. So electrons jump from the conduction band to the valence band. There will be no change in the momentum. So you will get light. Where in case of indirect band gap semiconductor, there's the conduction band minima and the valence band maxima. They are not lying with the same momentum or vector. So whenever they recombine, there will be some momentum changes there. So it generate heat, phonon, not photon. So this is the basic difference with the PN junction diode with the LED. So two things are there. It is the spontaneous emission, and we need to use the direct band gap semiconductor like gallium arsenide or indium gallium arsenide. These are the need to use. So and this spontaneous emission is from different energy level to the different valence level. So these are the bands. So bands are there are a lot of energy states are there. For this also the conduction and lot of energy states are there. So electron can jump from any state and combine with any state. So you have different energies and different output energy generated. So it may be each new one, each new two. So you have different frequencies generated. So you have the broad spectrum of light. Okay, so you have the broad spectrum of light. The spectrum is very broad of the LED. Whereas laser, you have the narrow band spectrum. Okay, where the deviation is very less. This is the center frequency, so the deviation is very less for the laser. For LED, the deviation is very broad. So in case of normal PN junction diode, as you can see, the spectrum is more broad because this spontaneous emission is not in your control, and also they can be recombined from the other regions also. Here also they can recombine. So light can be generated from here because the carriers are traveling from here to here. So they can recombine here also. They can recombine here also. So you can get different light generated from different parts of the semiconductor. So lot of the lights will be lost. You will not get confined light here. So that's why the heterostructure is used. The heterostructure can be used. So where you have two materials of different band gaps. So this is the smaller band gap material can be sandwiched between the wider band gap material. The gallium arsenide is band gap 1.42, and the aluminum gallium arsenide is band gap 1.92. So as you can see, this electron does not see any barrier from here to here. So if you apply, this is the inside and this is the p side. So if you apply positive voltage here and negative voltage here, p junction is forward biased. So electron does not see any barrier. So electron can flow from this gallium arsenide to this gallium arsenide region. This is the intrinsic region. So they are reaching in the conduction band. Now you can see these electrons here larger barrier from moving from here to here. So they cannot move here to here. They will be reflected back. So they will be confined here in this region only. Now this is for holes also. This is the p-type region. Holes are there. So hole is moving from here to here. So hole is saying a small barrier here. So hole can move from this p region to the here. And now this hole has here larger barrier in this region. So they cannot move in this direction. So they will be confined to reflected back on confined to this region. So you can see you can confine the electrons and hole only in this region. So the recombination can happen only in this region. So you will get more confined beam. So you will get more intense LED power. So in general, there is the heterostructures are used. So these are the non-emission diagram. This is the band diagram. This is the p-type and n-type. This is the depletion region. We have the barrier potential. This is the barrier potential. This is the barrier potential is there. So electron has a barrier in this direction, so you cannot move. You cannot move the barrier across direction. Hole has the barrier in this direction. So always electron barrier is in the upper direction and hole barrier in the lower direction. So hole cannot move overcome this barrier from p side to inside. And electron cannot move overcoming this barrier from inside to p side. So that's why this at equilibrium the carrier's movement is stopped. Now if you apply a positive voltage in this p side and negative voltage in inside. So this n side will be moving up, getting the negative voltage, and this p side will be moving down, getting the positive voltage. This potential will be increased here, and potential will be decreased here according to the voltage. So this barrier potential will be reduced. This is V0 minus V. This is V the applied voltage. So now electron can started to flow from this, overcoming this barrier. So hole also started to flow from this barrier. Okay, so electron can move from here to here, hole can from p to inside. So now they are moving, so they can recombine in this depletion region. Initially, this region is depleted of mobile carriers. There is no recombination here. So now the carriers have started to moving in this region. So they will be recombined and you will get the LED light. Okay. So this is the carrier distribution. So if you apply any positive voltage, holes are moving from p side to inside. So this is the whole concentration inside. So it will increase this direction because the holes are moving, diffusing in, and electrons are decreasing in from inside to p side. So this is the electron concentration in the p side. So that is also increased. Okay. So this increased concentration will be responsible for the recombination. They will recombine with the hole and electron available in this region. So this is the structure of the LED. As you can see, there are all these structure they are using the heterostructure. There are two types of LEDs there. One is the surface emitting LED, where the light is emitted to the surface, that is the perpendicular to the surface. Okay, and another type of LED is the edge emitting LED. So it will emit from the depletion either the active region from it. So these are the two type of construction you can make. So you can make the construction like this, so the light can be emitted from here and it can be emitted from here. Now, in practical cases, LED light are like this. They will be encapsulated in epoxy. Epoxy is used to increase the extraction efficiency of the LED light, and also it can be used to shape the light. This reduces the refracting index mismatch between the internal medium and the air medium. So it increases the extraction efficiency. Different types of epoxy types of lens are used. So one is this is the hemispherical lens. This is the parabolic lens. According to these two type of lens, your LED pattern will be changed. Normally, LED pattern is a Lombardian spatial pattern. It's all direction. So you can change the direction by these two structures. And these are some materials used for the LED. This is for infrared and red, orange, green. So these, depending upon the band gap of the semiconductor, you will get different light. Gallium nitride used for the blue light. Depending upon the band gap. So this is the band gap. So depending upon the band gap of the material, you will get a different waveform of the light. Okay. So this is C by lambda. So lambda will depending upon the band gap. So if you changing the material, if you change the band gap, you will get different colors of light and different wavelength of the light. So we have discussed about the LED before. Now we are discussing about the laser. So the full form of laser is light amplification by stimulated emission of radiation. It's the acronym of the laser. So light is amplified by the stimulated emission. Okay. So light is amplified means light consists of photons. So the photons are getting multiplied. So you will get large number of photons. So that is known as amplification. So we'll see. So laser is the coherent monochromatic light. Okay. Coherent means all the photons that generated they are in phase at the same frequency, so same wavelength, and they are traveling in the same direction. So the intensity is more compared to LED. Okay, and the intense beam, they are line width is small. So their spectrum which is very small. So it has more intensity, and it can be used for long distance communication. So and also it's a light intense beam. It can be used for treatment purposes also, and whatever you can communication purposes. It's a lot of applications are there. As you can see, the main is the stimulated emission. So we have already studied the stimulated emission. So what is that? So initially the light is absorbed. Okay, so this is the absorption. If the incident photon is matches with the band gap, the photon will be absorbed. Now, if the electrons are spontaneously emitted from the conduction band to the valence band, it will emit the photon with the energy equal to the band gap. Now, if a photon strike the electron, so the electron will jump from the conduction band to the valence band. It will generate a photon with the same energy and the same wavelength and same frequency of the incident photon. So this is the clone photon, which has the same wavelength and same frequency and same phase. So that is known as the coherent. Okay. So as you can see, the same frequency, same phase, polarization is also same, and direction is also same with the incident photon. Okay, so and also laser is also same, which work for the direct band gap semiconductor. Basically, laser is a optical amplifier. So you have the optical amplifier with the light getting amplified, and it will be feeded back to the input. So if the feedback path it's the same phase with the input, so it will get amplified, and it will generate to oscillate. So it's a feedback oscillator kind of thing. It's a optical oscillator laser. Laser is the coherent monochromatic light, and this is the energy diagram. So this is the ground state, the excited state, and has some metastable state. So electron are generally getting the energy, and they will move to the higher energy state. This is the short state, like time is 10 to the minus 7. So from that, they quickly jump to the some intermediate energy level state. This is the metastable state. Their lifetime is 10 to the minus t. So they can stay longer in this energy level. Now, if a photon is hit there, so this electron will come from the conduction band to the valence band. It will generate the same amount of photon energy that is hit, that incident photon. So the large number of photons are generated. Okay. So the main property of the laser is the gain, bandwidth, and the phase shift. These are the three main property, and these are the components of a laser. One is the gain medium, which provide the gain of the laser. So and the laser pumping energy is used for the pump. And that means the electrons are pumped from the valence band to the conduction band, and reflector is also needed. So that is used for the feedback purposes, and output coupler and the laser beam. So these are the different components of the laser, and it is also happening for the direct band gap semiconductor laser action. So how the laser will work? So if a photon if the photon hits this energy, this band, so it will generate two photons. Okay, right? So if you place a mirror here, so this photon will be reflected back. So these two photon again will hit the energy, okay, hit this material again. So that will generate four photons. So that will be traveling this direction. So again, if you can place a mirror here, so that four will be reflected back. So again, that four will be responsible for generating more photons. So in this way, you will get large number of photons generated. That all are coherent and that all are in same phase and same frequency, and they will travel in the same direction. So this is the gain medium. Okay, so that is why you can increase the gain. And these are the two positive feedback mirrors are used here. You can see this. So these are the mirrors. They will be reflected. The photons are reflected back, and it will again hit this medium. This is the gain medium. So more and more photons will be generated in this way. It will generate large number of photons. So these are the two reflecting mirrors. So this is the 95% reflecting mirror. So when it is reached 95%, then the laser will be coming out from this here. Okay. And if the length is L, so you can see this is 2 NL is equal to K into lambda. This is the emitted wave from emitted wavelength lambda. N is the refractive index of the medium, and L is the length of the cavity. This is the examples, ruby laser, the first ruby laser is 3-level laser. We will discuss it later. So now how the laser will work, as we have already told, it has some loss in this medium also. All the lights are not will be reflected back. This is not some light will be lost. Some electron hole will be recombining, so they will not generate any photon. So there is some losses in this cavity also. Now when the gain is overcoming the loss, then only we will get the laser output. Okay, so there are some lot of modes will be there in the, so the modes which support this gain is greater than loss. Only that mode will emit the light, and that mode will be supported by this cavity. Okay, so there are laser beam is very narrow beam, so you have intense light. Okay, so as you can see, this is the gain medium we have discussed. Now next is the pumping. So pump means, so as you can see, you need a large number of electrons in the higher energy level compared to the lower energy level. But electrons generally stay in the lower energy level. So they does not want to stay in the high energy level. They used to lose the energy and come back to the lower energy level. So you need to create that situation where you have more number of electrons in the higher energy level compared to the lower energy level. So this is known as the population inversion. So to create the population inversion, you need some extra energy. That is another pumping energy. So you need the pump energy so that the more electrons will be there in the conduction band. So that when the photon hits this medium, the electron can jump from the conduction band to the valence band. Generally it can generate the clone photon. Otherwise, the lasing phenomenon will not happen if there is not large number of populated state in the higher energy level. So you need this pumping energy. Okay, so to pump the carriers from the lower energy state to the higher energy state. So pumping to create the population inversion, that is N2 will be greater than N1. That means this is the higher energy state. The number of electrons higher electrons in N2, and this is the N1, the electrons in the lower energy state. So N2 will be always greater than N1 to have the lasing action. So we need pumping to create this because normally N1 is always greater than N2. So that's the normal phenomenon. Like electron will always stay in the lower energy level, but you need to create the population inversion to make the lasing action happen. So there are three types of pumping. One is optical pumping, one is electrical pumping, one is chemical pumping. You can optically make this happen, you can electrically make this happen, you can chemically make this happen. So these are the examples of the pumping. So this is the first one is the direct current. So you can using the electric current to pass through the material to make the pumping. So that electric current will give the energy for the electrons from the lower energy state to the higher energy state. Okay, radio frequency you can use for the same purposes. You can use some flash lamp, that is used for the ruby laser. You can use lamp. This is the optical pumping. This lamp or light will give the power for the pumping. You can use the laser diode to use to pump some other. This is the silicon EVM of silicon fiber. So this laser can be used to pump other for the to cause the other lasers also. Okay. So these are the different. This is the optical pumping. This is these two are optical pumping, and these are the electrical pumping. You can use the current, or you can use the RF source. Okay. So as you can see, this is the higher energy state. This is the lower energy state. Okay. So you can see that the electron can jump from this is the level 2, this is the level 1. So each electron can jump from level 2 to level 1, and they can jump from level 2 to level uh, 0 also. Okay. So what is the rate? This is the how the carriers are decay. This is the decay time or rate. So you can see this is the time. So rate is inversely proportional to the time. So this is the time of the energy level 2, that is related to 2 1. This is the uh, time taken from the state 2 to 2 1, and it will from the 2 to 0 to 0. This is the summation of these two. And 2 1 is one is the radiative recombination, one is the non-radiative recombination. It can be non-radiative recombined, it can be radiative recombined. So this will be sum of these two. Okay. So total rate will be sum of these two rate, and as you know, rate is the inversely proportional to time, so it will be 1 by time will be equal to this equation coming. Okay. So to have the population inversion, you need to pump the electrons to have the higher to stay in the higher energy level. Okay, so from that they will decay to this energy level 2, and they you have the population inversion. Okay, so you need to create that situation so that energy levels of above R2 will be filled, so that electron can jump from the R2, then jump from this above level to the energy level 2, so that the population inversion can be created. And also this one level should be empty, so this can release the electron and come down to the here. Okay, so these are the two things you need to make sure to happen. Okay. So as you can see, there are different materials have different mechanism for the lasing actions. So you can make it as a 4 level system and a 3 level system. So this is a 4 level system. You have the 4 energy levels. The lasing action is related with the four energy levels. So if you have the pump, using the pump, electron jump to these higher energy levels. So this is the short-lived level. So they rapidly decay to some intermediate level. This is known as the metastable state. This is the long-lived level, and from the long lived level they are they are moving down to this short lived level. Okay, and again from this short lived level is it can decay to the ground state also. So this 4 level system is not have the lasing with respect to the ground state. So lasing will happen from this 2 to 1 energy level. Okay, so he will have the laser from this energy level 2 to 1. Okay, so if the photon hits this system, so you have the population inversion in this energy level 2 and 1, so you will get the laser light here. So it include all the 4 energy levels. So this is the 4 level system. Okay. Now 3 level system, it will relate to the ground state. You have the intermediate state and the higher energy state. So you have the pump. The electron will be in the higher energy state, short-lived. They will rapidly decay to this intermediate state or the metastable state. They will long-lived, so it can stay long here. So if the photon hit this level, so you can have the laser from this two to one level. So this is the three level system. Okay. Now this is the ruby laser. This is the first laser. As you can see, this is the first laser is the ruby laser. So it is invented in 1960. So it's a ruby rod. Okay. So and you have the high intensity flash lamp is here. So this will give the pumping to this rod. So if you have the pumping, so electron will be energized to the higher energy levels. So and if they decay from the higher level to the lower level, so they will generate laser. There are some mirrors is also there. 100% reflecting error. This is 90% reflecting error. So the photons will be generated, they'll be reflected back, and they will create the positive feedback and the gain medium also. So you'll get a reflected light here. Okay, so this is the three level system as you can see here. Okay. So this is the ruby laser. Is the chromium arm that will replace some. This is aluminum oxide. Okay, this is the sapphire. So some chromium ion will replace the aluminum ion in this aluminum ion in this here. So it will make the ruby. So if you have the pump, it will be excited to the higher energy level. Then there is a short lived, it will decay to the long metastable state, and from that metastable state, it will jump to the ground state. You will get the light emitted here, laser light here. So it's a 694 nanometer laser. It's a ruby laser. So it's optical pumping with the flash lamp can be used. Okay. And another type of laser is the neodymium doped yttrium vanadate laser. Okay, this is the neodymium ion. It's a four level system as we have discussed already. So this pumping is 808 nanometer need to be pumped. So 808 nanometer it will be received and it will go to the higher energy state. Then it will rapidly decay to the this energy level state long state 2. So from 2 to 1 you will get this 1064 micrometer laser later emitted from this neodymium doped India yttrium vanadate laser. So and this yttrium vanadate laser and sometimes used with the lithium triborate crystal. So that is the fixed range frequency doubler crystal. So if it is pumped this yttrium vanadate laser is pumped with 808 nanometer. So these are the reflected back, and this is the 1061 nanometer coming out. And the light travel to this lithium triborate is a frequency doubler circuit. So you will get the wavelength 532. So you will get the 532 nanometer wavelength coming out from the lithium triborate. So this can be the frequency doubler circuit. Now, next is the EDFA. It's EDBM dot fiber amplifier. So, after this, we are talking about the laser. So, now we will talk about the amplifier. So there will be, if there is no feedback to the lasing action happens, so that can make amplifier. Okay. So if the amplifier have the feedback, you can make the laser. So erbium doped silica fiber lower. The silica fiber is doped to the erbium fiber, erbium ions. So ADBM science will be jump to the higher energy level by having the pump energy, so 980 nanometer. So and it is the three level system, so it can jump to this level, and you can have the laser or the amplification action from this uh, two level to the one level. So you'll get the wave from around 1530 to 1565 nanometer range. So if you have the incident waveform around 1565, you will have the lasing amplified. This input laser, this input light will be amplified. Okay, by this LVM dot laser. So this this can be used as single mode fiber communication because it can be used as amplifier. So you can for long distance communication use this amplifier because the light is lost from losses will be there in the optical fiber. So light will be get attenuated. So you need to amplify the light. So at 300 Kelvin, it's a three level laser. At 777 Kelvin, it's a four level laser. So basically, you have the erbium ions are there here in the level 2. If you supply the pump, 980 nanometer pump, so you have the erbium ion here. Now, if you incident light here, that erbium ions will be jumping from 2 to 1. It will generate the same amount of photon light that is incident here. So this incident light will be amplified. Okay, by this helium drop laser. So this is the basic function of this helium drop amplifier. So if you can make laser also from this helium drop fiber amplifier. So if you use some feedback with this amplifier, helium drop amplifier can be feeded back, so that can make a laser also. You have only one spectrum if you have the fiber backgrating laser, because the fiber backgrating will reflect only a specific wavelength that will support the black criteria. Laser is a, we can say, optical feedback amplifier. So this is the gain medium. And these are the two mirrors. So these mirror will be used to reflect this incident photon here. This is the active medium which provide the gain. So if the gain is greater than loss, then only you will have the laser action. So in this cavity, there are some lot of different modes are there. So you have this. If you have this is the frequency of the mode. This is C by 2L. This L is the length of this cavity. C is the velocity of the light. So number of modes is will be equal to this. This is the bandwidth. So B by this nu f. So you have only those mode that has the gain greater than loss. You will have those mode only emitted from this cavity, and that will be responsible for the lasing action. And this is the semiconductor laser. It's heterojunction is same as the LED. Okay, so light will be emitted from here, and you can see the two surfaces. These two surfaces are mirror polished, and they are clipped to work as a mirror. So you have this refractive index is different from the compared to air. So the light emitted has the total internal reflection again from this semiconductor and the air surface. So light will be reflected back. So these two sides are act as a mirror for this semiconductor structure, and it's almost like a same of the LED. But in case of LED, you don't need the population inversion, but in case of laser, you need the population inversion. So for that, you need to make the active region as small as possible compared to LED. So if you make it forward bias, the large current will be flowing in this smaller active region. So the electrons from the valence band will get that energy and jump to the conduction band, and due to the heterostructure, it will confine to the higher energy level. So it will create the population inversion. So you will have the lasing action. Okay, so for the LED to laser, you need to make the dimension smaller, you need to make the active region smaller, and you need to pass the high current through the smaller region to get the population inversion. And you will also need the mirrors. So these two surfaces are used as a mirror. This is a clip surface. The light will be reflected back, so you have the lasing action in between. So the light will be emitted from this semiconductor. This is a semiconductor laser. So we have discussed laser. So now we are moving on to the photodetector. So photodetector means it will detect the photon. Okay. So you can detect photon by converting photon to the electric current or heat. So when the photon is converted to the electron current or electron is photoelectric effect, and when it is converted to heat, it's a photothermal effect. Okay. So photothermal effect is for the air imaging. So if the light some materials light is absorbed and it will convert to heat, so that heat can be used for the imaging purposes, thermal imaging, medical imaging. So these are the photothermal effect. And photodetector application is biomedical application, medical imaging, optical communication, and the camera. Optical communication is you need to detect the light. You are sending whatever you have studied, you are sending the light to the optical fiber, which study the how you generate light using LED and laser. But you need to detect the light, right? Because we are dealing with the electrical signals we need to deal with, right? So we need to convert that light into the some electrical or measurable quantity so that we can measure and do our process. So that light need to be detected and need to be converted with some other form. So photodetector will convert that photon energy to some measurable form. Okay, so measurable energy form so that we can measure. Kind of a transducer, you can say. Yeah, it's convert one form energy to another form of energy. So light is absorbed when the photon energy is equal to the bandgap of the energy. So it will generate electron and hole pairs. So that electron and hole pair can be swept with the electric field. So the carriers can be moved and you will get the electric current. So that is the measuring property. Okay. So photoelectric effect can be termed as two types. So external photoelectric effect and internal photoelectric effect. Internal photoelectric effect means the electron, whatever is generated absorbing the light or photon, it will stay in the conduction band. Okay, they are not coming out from the conduction band to the vacuum. So this is known as the photoconductivity. Okay, and this is the photodetector how they work. So electron are moving from the valence band to the conduction band, they will stay in the conduction. They are not coming out from the conduction band to the vacuum. But the external photoelectric effect is the photoelectric emission. So the electrons are emitted from the conduction band to the vacuum. This is mainly used for the metals. Okay. So the electrons are emitted from the conduction band to the vacuum. So for the metals, we have the work function. Work function is defined as the minimum energy required to move an electron from the Fermi level to the vacuum. And for the semiconductors, we have defined the electron affinity is the minimum energy required from an electron to move from the conduction band to the vacuum. Okay. So this is the relation for the energy. So Einstein equation is H nu minus W. W is the work function. This is the excess energy you need to supply. And this is the H nu minus W is the emax. Maximum energy you can supply for electron to escape from the metal to the vacuum. And Planck and Max Planck and Einstein, these are the two main contributors of this quantum optics and quantum. So Einstein is first explained this photoelectric emission from the metal. Okay, so on that it's explained that light consists of some particles. So if the particle hits the metal, it will generate some photon particles. Now, for semiconductor, the Emax will be H2 minus work function W. So for intrinsic semiconductor, we can replace the W by chi is the work function, and this is the Eg by 2, so band gap. So Fermi level for intrinsic semiconductor lies at the middle of the band gap. So it's Eg by 2. So it's H2 minus pi plus Eg by 2. This is the Emax. So photoelectric emission, there are two things is there. One is this is the phototube and one is the photomultiplier tube. Okay, so phototube is the is the material plate is there. So light is emitted, light is heated this metal plate with generate electron and hole pair. You have the anode. The light is attracted by this anode. This is the anode making positive and cathode is making negative. So electrons will be generated. Electron will be emitted from this metal plate. It will be attracted towards this anode. So this you will get a current, okay, from this photoelectric emission. Now, if you can use this anode or the electrode as this is the total reflect work as a reflected mode. Okay, you can make it a transmission mode also, so that it can this electron can be transmitted from this electrode to the that electrode. Okay, and if you make this electrode as a higher potential, so that these electrons are hitting this electrode surface also. Okay, those say light is heated here, so one electron will be generated. So it will be traveling and heated this electrode, so it will generate two electrons. These two electrons will be coming here. It will generate four electrons. So it's a cascade kind of thing, and it will generate multiple electrons. Okay, so this is the multiplication of the electrons. This is the photomultiplicative, so you will get large number of electrons, so you will get a large current. Okay, so these electrodes are known as the diodes. They are kept at a higher potential, so that electron will be drifted at a high velocity, so they can heat and generate a large number of photons. So these are the two they are the two types of the photoelectric emission. One is the phototube, this is the photomultiplicative. So this is the its gain is high. It can operate at higher power, and it can detect some and see some low power light also, because you get large number of currents. Okay, so you get large number of current as well the output compared to this photo tube. Okay. So now we'll move on to the photo conductor. So photoconductor is basically a photodiode. So it's made of semiconductor. It's a PN junction diode. So as you can see, if you have a PN junction, so you have the depletion region here. This is the uncovered immobile ions. This side you have the donor ions. You have positively charged. This side have the acceptor ions, negatively charged. So you have the electric field from this N side to P side, and you have the depletion region. So this region is depleted of mobile charge carriers. Okay. So now if the photons is hitting this surface, it will generate electron and hole pairs. Okay. So it you have the internal electric field that is from N side to P side. So electrons will be directed in this direction, and holes will be directed in this direction. Okay, so electron will be directed from left to right, and hole will be directed from right to left within this internal electric field in the depletion region. Now, if you apply a external voltage, okay, external voltage here, so the electrons whatever generated by the incident photon, they will be drifted in this direction, and the holes will be drifted in this direction. So electron will be traveling in this direction, and hole will be traveling in this direction. So we'll get the current at the out. Photodetector is always operated at the reverse bias condition. While LED and laser, they are operating in forward bias condition. These are the major two differences. LED and laser, you need to connect in forward bias condition, so that the electrons and hole will flow in this junction, and they will recombine, and you will get the current, and you will get the light. Okay, so and the for photodetector you need to connect in reverse bias condition. Okay, so that whatever the electron hole pair generated in this depletion region of the junction, they will be swept across this semiconductor to collect, so you get the photocurrent. Okay. So this is the Venn diagram. Reverse bias, you have a higher varied potential, so there will be no diffusion of carriers. So there will be, if the diffusion is not there, you will not get any diffusion currents. All the current will be for the photocurrent is there, and the drift current is flowing also for this, but they are the magnetic carrier currents. If you have the holes are here, so hole will be this is the positive hole will be traveling in this direction, and it will traveling in this direction, so you'll get a current in this direction. This is the magnetic area current. This is very less, because it's dependent on the magnetic area. So whatever the current you will get is depending upon the incident photon of the light. Okay. So if you light is incident in this semiconductor, you will electrons will be jumped from the valence band to the conduction band, and you will get the electron and hole pair, and that will be swept by this applied voltage, and also with the inbuilt electric field. Okay. So but this photodetector is normal PN photodetector has a smaller depletion region width, so your incident photon absorption is very less. So the efficiency is less for this photodetector, because less number of photons gets absorbed in this depletion region. Most of the light will be lost when we travel here and there. So we need to make the depletion region wider. Okay? So so you need to, if you make large dividers, you can make it wider, but you cannot make a large divider because at the time it can be breakdown, or it can be within extend the limit of the power rating of the devices. So the solution is we can make a pin type. So basically we insert an intrinsic material between this P type and N type, so that this total intrinsic material is work as a depletion layer. So now your depletion region, which is very large, you can emit the light, so the absorption is more, so it can be absorbed on this longer length. So your depletion region is more, so more light will be absorbed, so you will get more current. Okay, so your efficiency will increase for the photodetector. Okay, and the performance will be improved. So our depletion region is now this much, so you have the photon is emitted, we have the electron and hole pair will be generated. So electron will be drifted in this direction, hole will be drifted in this direction. So we'll get the current. Okay. So if electron is moving in this direction, we will get the photon current in this direction. Okay. Current is opposite to the flow of the electrons. So if you are applying reverse bias, so your height will be more, diffusion, sorry, barrier potential will be more. So this is the diagram, and this is the charge storage. This side inside is positive, this side is negative. This is the donor arm, this is the acceptor arm. So this is the electric field. It will be constant to the depletion region, and it will decrease towards the end. It will increase towards the end. It will like this. Okay, it's from inside to inside, so it will increase in this direction. Okay, so this is the structure. So you have the input performance here. Okay, so but you cannot make this then larger because it will slow up the device. Okay, because the speed of the device is depend upon the transit time. So transit time is basically this WD by the velocity, drift velocity. Okay, so if you make uh, W is W more, so you will get the transit time more. So it will take more time to carrier to travel. Okay, so your device will become slow. Okay, so that's the trade-off is there, and so you need to trade off the width so that your speed will be not less, and also the it will depletion region will become larger, and also the speed is dependent upon the RC time constant. So your capacitance is epsilon by W. So if you make W large, your capacitance will be less. So it will decrease the capacitance, speed will be increased, and also the transit time is increasing because your W is increasing. So W by V is the transit time. So that time is increasing. So this is the trade-off you need to make the width. You cannot make large. You cannot make it too small also. Okay, so that's the trade-off thing you need to make and you have to consider also. So next is the APD, is the avalanche photodetector. In case of photodetector, you have only the photo-generated current, but in case of AVG, you have the avalanche multiplication happening in this. This is the heavily doped semiconductor layer is there between the PI, and this is the PI N structure. N is the heavily doped. You have the lightly doped region, so you have a high electric field in this P and N plus region. If doping is high, so electric field will be high from N to P. So the whatever the electron hole pair is generated, they will be drifted by this electric field. Now, if this electric field is high, so it will enforce more force to these electrons. Okay, the carriers. So that electron can hit in traveling, they can hit other electrons and they can give the momentum energy to other electrons, so that electron can be excited and that will generate another electron hole pair. So those electrons again will be drifted by this electric field, and that will generate more and more electrons. So this avalanche multiplication process, this is a cumulative process. So electrons will be drifted from this p side to inside, whatever generated by the photons. So they will be colliding with the other electron hole pair, other bonds. So that will break the electron hole pair bonds. So it will generate more and more electron and hole pair. So it will generate more electrons. That will be again generating more electrons by the avalanche multiplication. So this is the avalanche photodetector. Its gain is more compared to the photodetector. So when you need more gain, you can use the avalanche photodetector. As the gain is more, it can detect. You can make a small light also, you can get larger current. Okay, so this avalanche photodetector operates with large reverse bias condition. You need to apply large reverse bias voltage. Okay, to make this breakdown happen or the avalanche multiplication happen, you need the large reverse bias voltage. This voltage need to be high. Okay, so this is around 140, 150 volt you can apply. Okay. So this is avalanche multiplication, avalanche photodetector. Another one is MSM photodetector. This is another type of photodetector where this metal plate or interdigital structure, you can make the top surface here. So light will be entering like this. These metals are alternate positive and negative. So whatever electron hole generator, they will be drifted by this metal plate. So positive and negative. This is positive. This is negative. So we have alternate positive and negative metal structure. So that can be drifted. This is the planar structure easier to fabricate. That's why this photodetector is uh, is growing now. And also the one thing is that you have the metal plates are low, so therefore the responsivity is less. So more light will be lost in these metals. They cannot reach the semiconductor. So these are the things. You can use transparent electrode also, so that I can be transmitted through this transparent electrode and can reach the semiconductor. So more light can be absorbed. So that the trade-off is there. So more research is going on in them also. So now the figure of merit of the photodetector means how we can measure the performance of the photodetector, how we can compare whether this photodetector is good or bad compared to the other one. So these are the parameters. Sensitivity. Sensitivity means how sensitive it's with respect to the optical power. Okay, means how effectively it can convert the optical power to the electric current. So how sensitive is to the light. Okay, and efficiency means how efficiently it's converting that number of photons to the number of electrons. Okay, that contribute to the current. So the efficiency. And response time, we need to high response time because it's high frequency application. We are moving to faster and faster communication systems. So the response time will be less. Otherwise, you cannot detect the light, whatever you are transmitting. And signal to noise ratio, when signal to noise ratio should be high, and the reliability should be high. Cost should be low. as much low. So, and dark current is also related to the sensitivity part, or you can say, because dark current is whatever the current you are getting without the light. Okay, so that means the whatever reverse current you are getting, reverse saturation current due to the magnetic field. So it should be as low as possible. If it is low, then we can detect a smaller amount of light also. Because if the dark current is high, if you shine the light, you will get the current, but you don't know the current is for photo generated for the photon, or the it's generated due to the magnetic field. So magnetic current should be low so that we can detect the minimum amount of light. So these are the thing, and the efficiency is related to this. IP is the photocurrent divided by E, is the electron charge. So this is the number of electrons contributing to the current. This is the generated number of electrons, and this is the P, the incident power, is nu, is the photon energy. So this is the number of photons incident. Okay, P by H nu. This is the efficiency, means how efficiently it can convert the photons to the electrons. And this is the responsivity, is related to photocurrent divided by power, input optical power. So uh, how quickly it can respond, so how the sensitivity of the photodetector, so that it can convert the photon energy to the current. Okay, so if you shine the photon energy, how sensitive to this photon, so that it can generate the photocurrent. So this the responsivity is the ratio of the photocurrent to the incident power. Okay, so that can be expressed as n eta into lambda by 1.2. It has efficiency, lambda is wavelength. So this responsivity is linearly proportional to the lambda. So as the lambda is increased, responsivity will increase. Okay, this is the incident power. It will be related to the absorption power is 1 by e to the power minus alpha. So alpha is the absorption coefficient of the material, and x is the distance. Efficiency is between 0 to 1, and there are some losses also, because all the light will be not be absorbed, because some light will be transferred to this medium also. Some will be reflected back also, and whatever the electron hole pair generated, they some will be recombined here, so some will be lost whether before they are connected to the contact. So these are the some losses in the photodetector. So before reaching to the contact, the electron hole pair will be lost due to recombination, and the light will be reflected back also, and some light will be transferred. So all the light will be not contributing for the generation of electron hole pair, and all the generated electron hole pair will not contribute to the photocurrent. Okay, so these are the losses, and gain is defined by this. Combination time should be more compared to the transit time. So you need to make the transit time low. So you need to make the length low. That's why I'm talking about that. You cannot make this W as large as possible for the incident photon to absorb a lot of photons. At that time, if you make the L large, you will transit time will be become very large. So it can become you will yeah, transit time will become large, so your gain will be very less. Okay, so your transit time will become large, so gain will be less. And if the transit time will become large, also you will get a slow response. So if you cut the responsivity with the wavelength, practically it should theoretically it should get a straight line, but you will not get a straight line. You will get this type of cut. It will increase, then after some certain limit, it will decrease, because after a certain wavelength, length is increasing, so your energy will be decreased. So that energy is less than the bandgap, so that light cannot be absorbed. So your responsivity will be becoming less. Gallium arsenide, they are different responsivity. So same type of structure, you can find the light. Whatever the light will be absorbed, they are different compared to the different materials. So you can use different materials. Generally, gallium arsenide has the higher responsivity compared to silicon. So gallium arsenide can be used for the high speed, high purpose computers. So you can make smaller devices. So you can make if you make a small device compared to silicon, gallium arsenide can receive more light compared to the silicon. Okay, camera has the photo detector. You can detect the light. Basically, when you're capturing the photo, the light is coming through the lens, and it will be captured, detected by the photo detector. So basically, pixel is a photo detector. So as the pixel is increasing, number of pixels increasing, you have the number of photo detector is increasing. So basically, you have the photo detector here. Okay, can insert the lenses also. For the black and white, you have the mono lens, and for the you have the color filters for the color lens for the color filters. So this is the 50% green, and 25% blue, and 25% red. This is the color filter. So these color filters are used to absorb the light. It will green light, and this is blue light, this is red light, and they absorb. So accordingly, they will you will get the color image. So this is the lens, and this is the photo detector. In between that, you have the filters. So this is the color filter, 50% green. As you can see, this is the 50% green is there, and the 25% red and blue. This is the Bayer filter we use. This is the Bayer filter. So that can be detect the color light. This is the black and white for the camera. So this is all for the camera purpose. So that's all about the photo detector. Next, we will move on to optical modulators. So optical modulators is a device so that can change the light phase, okay, amplitude, polarization, time, direction, wavelength, frequency, and polarization. Okay. So modulators can modulate these all the properties of the light. So these are the some examples is given. So here is the amplitude is modulated, the value got reduced, can modulate the phase. So you can modulate both. So we can classify the modulator in two broader aspects. One is absorptive modulator based on the absorption principle, and another is the refractive modulator. This is related to the refractive index changes. Okay. So refractive modulator can be classified into electro-optic modulator and the acoustic modulator. Acoustic modulator is refractive index will be changed with some acoustic wave, and electro-optic modulator means you can change the refractive index with the change in the electric field. So electro-optic modulator can be classified as phase modulator. You can modulate the phase, you can change the phase. Amplitude modulation, you can change the amplitude, and lastly the polarization, you can change the polarization also. So you know that we have studied about the retarders. So there are one kind of modulator because they can modulate the polarization, so they can change the polarization. Okay. And here it is shown the Mach Zehnder, so that can be used to change the phase of the light. Okay, so you get constructive and destructive interference in the output, so it can be used as a phase modulation. So we will first discuss about the acoustic modulator. So here sound waves is used to modulate the light. So if sound wave is sound is sent through any medium, so the refractive index of the medium got changed. So accordingly, the light will be reflected or transmitted depending upon the refractive index. So this is the refractive index profile. So where the sound wave is making the compression of the medium, where the and other places is got rarefaction. So in the compression medium, refractive index is more, and rarefaction medium, the refractive index is less. So you will get a very varied refractive index profile in this medium. So now when the light is transmitted through this medium, and you have sounders. Sounders basically acoustic waves, so that can generate stress in this medium. So that stress can change the refractive index. So you got the periodic refractive index structure. So when the incident wave is incident in this structure, it get some portion will be get transmitted and some will be refracted back. And whatever light will be refracted as related to the Bragg's condition is the Bragg's getting Bragg further and some they have invented this. So depending upon the satisfying, if the wave satisfied the Bragg's angle, so it will be totally reflected back here. So this is the Bragg conditions, and it is a lambda by 2 del lambda, where del lambda is the period of the grating. So incident light will be depending upon the condition, it will be transmitted or it will be diffracted back. So if it is totally diffracted, whatever the way to satisfy the Bragg condition, you will get light from here. So you will not get any light from here. So you can say that the position of the light is also changed. This transfer initially it was in this position. If it is there is no medium here, and to this if it is traveling to this medium due to this acoustic change of the refractive index, it will be deflected in this direction. So the position is changed also. So if you can place the detector here, you can detect the light without this medium, and you can now you need to place the detector here, so to detect the light. So it can called as the position modulation also. So using this light intensity can be modulated. If you have intense light, it will pass through this grating structure, Bragg grating, and depending upon the reflection, depending upon the sound wave you are giving, this material will change according to this. So you will get the output waveform according to that. Now, if you give a electronic sound means if you change this sound to the some electric voltage or something like that, so it's 1 0 kind of thing. So accordingly, if you give the incident light, so you will get whenever the sound wave is high, so that will be reflected back. So that depending on the Bragg's function, so you will get output high in this position. And when the sound is 0, you will not change any refractive index change. So light will be transmitted through this medium in its initial position. So you will get light in this position. So this is the transmitted light intensity. This is the reflected light intensity. Depending upon the sound intensity, if it is high, you will get the reflected light. You will not get transmitted light, and if it is sound intensity is 0, so you will get the transmitted light. You will not get any reflected light. So in this way, you can modulate the incident light with this sound. So this is known as the acoustic modulator. So you can say the reflected light is proportional to the incident of the sound. It can act as a switch also, as you can see, it's on-off switch kind of thing. So and also you can say it's position. It can modulate the position of the light also. Initially it is this position. Now it can be changed to this position. So this is all about the acoustic modulator. Next we move on to electro-optic modulator, where the electric field is responsible for the changing refractive index. So some material has this property that if you apply electric field there, so their properties get changed. So the refractive index of the material will got changed. So the refractive index is related to the electric field of this relation. So as you can see, there are linear terms and there are non-linear terms also and higher order terms also. So if the electric field intensity is not much high, so you can neglect the higher intensity also. So electronic modulus is it can be used in Mach Zehnder for optical switching purposes. Okay. So if you send the light here, it will be divided by these two branches, and if you have any material that exhibit this electro-optic property, if you apply voltage, the refractive index of this material will change. So the velocity of the light in this region will change. Accordingly, your phase difference will be changed. So at the output, you will get the constructive interference or destructive interference depending upon the phase difference. So in this way, you can modulate the light, this incident light, with respect to the voltage. Okay. So whenever you are applying voltage, refractive index will be changed. So we'll not get any light, and whenever the voltage is zero, we'll get a light, or reverse vice versa also. So in this electro-optic effect, we have the two types of effect. One is Focal's effect, and one is the Kerr effect. These two scientists have derived these properties. So Focal's effect is related with the refractive index relation with the applied electric field. So had the refractive index change is proportional, directly proportional to the applied electric field. So it's a linear relationship. As you can see, if you plot the refractive index with respect to electric field, it's a linear relation. So this is known as the Focal's effect. So some materials have the Focal's effect, like lithium now that has this Focal's effect property. So you can use that. And Kerr effect is that when your refractive index is changed non-linearly with respect to the applied electric field. Okay. So this term is there. So there is a non-linear relation between this refractive index profile. So refractive index will change non-linearly with this electric field. So this is known as the Kerr effect. These are the two types of effect of the electro-optic modulator. It is also can be used for the modulation of the light. So last is the electro absorption modulator is related deals with the absorption of the photon. So some material has the property that if you apply electric field, their band gap will get changed. So initially, if the light is not absorbed by this medium, due to the band gap difference. So now the band gap is changed, so it can absorb the light. So this way you can make a electro absorption modulator. That's if you can change the electric field or voltage, that electric field will cause the band gap change band gap narrowing, so the light can be absorbed. Okay. So when the light will be absorbed, if this matches with the band gap. So initially when the electric field is off, the light will be transmitted. It will be not absorbed. Okay. So you got the transmission peak. Now if you apply electric field, that it will narrow the band gap. So now this band gap is equal to the incident photon. So now the photon is absorbed. So you will not get any transmitted light. So in this way you can modulate the light. So this is the incident beam, and this is the material who has the property. If we apply a voltage, so if when you are applying voltage, the light will be not transmitted. Okay, and when the voltage is off, light will be transmitted. So this way you can modulate the light also. So this all about the electro-optic modulator. So we have moved to the last topic, so nonlinear optics. The last topic of this course. So nonlinear optics means if you assign an input light to a molecule, so whatever light will be emitted, the wavelength of frequency will be different compared to the input. Okay, so this KDP crystal, lithium niobate crystal, CDSE crystal, lithium tribrate crystal, these are the materials, and other materials also they have this nonlinear property. So we'll discuss it now. So linear optics is deals with the weak light. Okay, so in linear optics, the frequency of wavelength is unchanged. So whatever the input or emitted, both the frequency and wavelength will be the same. So, and in case of nonlinear optics, it deals with the intense light or the high intensity light, so that intensity of the light is almost almost comparable to the interatomic electric field strength, that is around 10 to the power 8 volt per centimeter. So it can change the configuration in between. So if you give an intense light, so in the molecule will emit different wavelengths. So that's basically a nonlinear optics. So nonlinear optics is behavior of light in nonlinear media. So we have derived the relation of the polarization vector with this electric field that's related with the susceptibility chi. So you can, in general, you can write this polarization vector in terms of this equation, where pi one, pi two, pi three, these are the coefficients. So you can say that the polarization vector is nonlinearly responding to the electric field in these mediums. Okay, so if you shine the light, the applied electric field of the light will change the polarization, and this polarization will affect change with non-linearly with respect to the incident light. So, so chi1 is the linear relationship. So, in case of if the light intensity is low, these higher order terms will be neglected. So, we have only these relations. And if the light intensity high, so higher order terms will be coming up. So, you have the non-linear relationship with the polarization factor with the light electric field. Basically, it's a nonlinear media where the dielectric polarization is respond nonlinearly to the applied electric field of the light. So, if you have this nonlinear activity, you can have different kind of generation, like second harmonic generation, third harmonic generation, forward mixing. So we'll discuss one by one. So as you can see, these are the relations. So if the light is polarization is linearly related to the electric field, you will get a linear relationship like a straight line. And if it's non-linear related to the square and EQ, you will get this non-linear relationship. So when the incident light is intense, then we have the non-linear activity, non-linear processes. So the first one is the second harmonic generation. As you can see, this omega 1 and omega 2 is the two input wave. So at the output, you will get omega 2. Okay. So now the third harmonic generation, you need in the three pumping. So this omega 1 will pump this electron to this intermediate energy level, then another wave is needed to pump to this intermediate energy level, and another wave will pump to the higher energy level. So at the output, we will get this omega 3, that is the 3 of omega 1. In this case, omega 2 will be 2 of omega. So this is the second wave generation, this is the third wave generation. So this second harmonic generation, or you can say second harmonic generation, is the frequency doubling property. It is here when the ruby laser is signed in this KTP crystal. So you will get the frequency doubling output. This crystal will react non-linearly with this laser light. So you'll get red laser light 694 nanometer. Output you will get a C9347 nanometer. So it's a frequency doubler. Same thing will happen if you assign the laser light of the neodymium yttrium garnet 1.06 micrometer with this Ge and phosphorus doped silicon fiber, you will get the frequency doubling also. So these are the optical nonlinear phenomena. So second harmonic generation, sound frequency generation, frequency generation, and the n-wave mixing. So this is the sound frequency generation where output from output frequency is the sum of the input frequencies omega and omega 2. So at the output, we will get omega 1, omega 2, and omega 3 both, where omega 3 is the sum of this omega 1 and omega 2. So this is omega 1, this is omega 2. So at the output, we will get the omega 3. So two different pumping are there. So this omega 1 and omega 2, two different pumping for the different energy pump to the different energy level, the higher energy level. And from higher energy level, it will going to the lower energy level. So you'll get this omega 3 at the output. So tunable radiation in the spectral region, and this is the difference frequency generation where output omega 3 is the difference between this omega 1 and omega 2. So if you give this omega 1 omega 2 to pumping to this system, so at the output you will get this frequency of light is omega 3, that is the difference between the omega 3 omega 1 and omega 2. So this is omega 1, this is omega 2. So omega 3 will be equal to omega 1 minus omega 2. This is the difference frequency generation. And the last one is the four-wave mixing. So you need two pumpings, that's omega p and omega p, these two pumping. And at the output, you will get this omega p. This difference is sigma. So omega p minus sigma, and this will get omega p plus sigma. So this is the mixing of four waves. So you can say these are the two input frequencies omega p, and at the output you will get omega p minus sigma, and this is omega p plus sigma. So you get a lesser frequency and you get a higher frequency. This is the four-wave mixing. And we have already seen the nonlinear activities like the optical card effect, where the refractive index is changing nonlinearly with this electric field, so it's nonlinear effect. And we have studied about the fluorescence, where if you shine the input light, and you will get different output light from this fluorophore. So that is also a nonlinear property. And also in the yttrium laser, we have seen that we have used the lithium triborate LVO for the frequency doubling. So that's also another nonlinear phenomenon. This phenomenon we have discussed. So the another two main nonlinear phenomena is the one Raman phenomenon and this simulated Boolean scattering. So light will interact with the atoms and it will scatter from there. So there are two types of scattering. So if the incident waveform and the scattered output of frequency is the same, it's a Rayleigh scattering, and if the frequency got changed, it is fall under Raman and Brillouin scattering. So the Rayleigh scattering is in under the elastic scattering, and the Brillouin scattering or Raman scattering is the inelastic scattering, where it will interact with the material and some energy transfer will happen with that material. So when the light enters a medium, several different scattering mechanisms are possible, as we already told. Rayleigh scattering, when both input and output frequency are same, and Raman-Stokes scattering. So this is where the input and output, and Brillouin scattering also the output frequency are different. So in case of Stokes scattering, as you can see, this frequency is less to the input frequency. So the some energy is lost to the medium. And in anti-Stokes scattering, the medium or the material is supplying some energy to that. So you will get higher frequency compared to the input frequency. And also Brillouin scattering, you can see the again some energy is lost, but this change is the less compared to the Raman scattering. There are two types of scattering. One is elastic scattering, one is the inelastic scattering. And the main difference between them is the exchange of energy with the medium. Okay, so in Rayleigh scattering there is no exchange of energy, and Raman and Boolean scattering there is the exchange of energy with the medium. So as you can see, this is here the energy is supplied, that's why the frequency or energy is higher compared to the input, and here the energy is lost, so the output frequency is less compared to the input. And here Boolean also the same thing, but in case of Boolean and Raman, Boolean has the less exchange of energy compared to the Raman scattering. So now Raman scattering, if you shine a monochromatic light in the sample, so light will be scattered. So accordingly, we'll get this type three different waveforms. So one is the anti-Stokes, where the frequency is more compared to the input that we have already discussed, and the Stokes scattering. So where the frequency is less of the input frequency. So anti-Stokes, yes, this is the output scattered frequency is more than the input frequency, and this Stokes scattering, the output frequency is less than the input frequency. So these are the diagrams. As you can see, if this energy difference is less compared to the input, so you will get less frequency. If these two energy difference are same, you will get the same frequency. It's Rayleigh scattering. And here the output the energy is more compared to the input, so you'll get a higher frequency compared to the input. Boolean scattering is deals with the interaction of the light with the lattice vibration, and when the Raman scattering is dealing with the light or interacted with the molecular vibration. As you can see, the Boolean scattering, the shift frequency shift is very less compared to the Raman scattering. So this is the Rayleigh. Rayleigh scattering had the input frequency and output frequency both are same, and this is the Boolean frequency. The shift is less as the interaction of the energy with the energy with the material is less. And Raman scattering, you will get a large frequency difference with this input frequencies and order of 10 terahertz. These are the applications of the nonlinear optics. It is used in the pharmaceutics also. They used to check the medicine composition whether it is right or not by checking the Raman scattering. They will shine the light and they will check the scatter wave and they will check Raman scattering if the composition is right or not. So this is all the topics that have been covered through this course. So into photonics. So I have tried to cover the entire course in this video and whatever I have learned to share my knowledge. And I would like to thank Shivananji sir for encouraging me to make this video. So I've learned a lot from the class, a lot of new things that will help me. So I've tried whatever I have learned to explain, whatever I have understood. So I hope I make the video as per my understanding. So I hope you all will like the video. Thank you.